Good morning, good afternoon, and good day. So we are making this video to report the activities of the project CoMetaS in the framework of the Marie Curie program. My name is Luis Barrales. I'm a professor and researcher at Georgia Tech Europe and the CNRS Metz in Metz, France. Um, in the framework of this project, I visited Georgia Tech in Atlanta in the period indicated here. I was welcomed by Professor Surya Kali in his research group, and for this I would like to begin this presentation thanking him for his hospitality and numerous scientific discussions with him and members of his group. Thank you very much. So we have a very an excellent stay in Atlanta, and a lot of scientific research was performed during this period. In this presentation, I will give you first an introduction of the project. So essentially, I'm going to explain what we are doing here. In addition to that, we are going also to present the activities during the stay, and these activities entail essentially the simulation and modeling of the microstructure in additive manufacture materials. So we are also going to present one case of study, and we're going to finalize with the conclusions of this part of the project. So to begin with, here we have the general objectives of the CoMetaS project. So in this case, what we would like to do is to simulate or essentially to optimize the fabrication of additive manufacture materials, so what we call metamaterials. And to this aim, so we're going to utilize a strategy that entails the application of simulation models, experimentation, and also the formulation of surrogate models. And by doing this, so we expect also to optimize and to accelerate the design and utilization of metamaterials for different components and different applications. We also aim in the framework of this project also then to accelerate then the knowledge transfer. So and by doing essentially the secondments of the project, we expect then to educate numerous scientists that are going to be able then to utilize different computational techniques, different experimental techniques, and also why not utilize also some artificial intelligence then to accelerate then the design of materials. Uh, in our project, so in the part that corresponding to the project that we're performing then in the secondments in Atlanta, so we have developed constitutive models for 3D printed materials. In particular, we have developed a crystal plasticity finite element model to predict the mechanical properties of these materials. So these models, so they require the information regarding the structure of the material, or better say the what we call the microstructure. So the microstructure itself, it is the aggregate of crystal defects, orientation, and phases of the material. This information is necessary because the microstructure itself provides the state variables for the constitutive equations. Okay, and for that reason, so we must obtain this information either from experiments. So in this case, here we would require them to perform a perhaps EBSD, or also from simulations. Simulations in this regard, so they have the advantage that they can generate data at faster and cheaper rates than experimentation. So for this reason, in the framework of this project, so we have also developed a model for microstructure prediction. At the conclusion of the project, so we expect also to combine these two models and formulate what we call surrogate models by means of process structure properties relationships. Okay, so here we have essentially the objectives of this work package. So in the first work package, we're going then to implement a crystal plasticity model. And in the second work package, so we're going then to develop then the code for homogenization. The code for homogenization is necessary because in this case, we're going then to reduce a problem which is multi-complex, so many different processing parameters that are going to affect the evolution of the microstructure, and the microstructure itself is also going then to influence the mechanical properties of the part that we're trying then to fabricate. And for that reason, it's extremely important then to be able then to reduce then that complexity. And for reducing that complexity, we need to utilize then different mathematical techniques compared then to those that we utilize, for example, for the simulation. Okay, and this is what we aim to do at the end of the project. So at the end of the project, so we expect then to have the tools necessary then to be able then to predict then the final properties of a component given certain set of processing parameters. Okay. Excellent. So in metal additive manufacturing, so we utilize metallic powders and a heat source to melt local volumes of powder that upon solidification allow building a component layer by layer. Okay, so this technique is very well known for plastics, but recently it has also been utilized for metallic parts. Okay, additive manufacture has become a very relevant industrial process, and we expect that in the future this process is going to be even more relevant. After solidification, the microstructure has been found to diverge from the microstructure found after conventional processing. The reason for this is because solidification, right, and also because of the application of the laser. So the material is subject then to very high cooling rates. In addition, there is a very directional flow gradient, heat flow gradient, and for that reason, the microstructures show characteristics that are not usual in conventionally processed materials. So for example, rather than we usually observe columnar grains, but depending also on the processing parameters, so there are different microstructures that we may expect. However, so as I mentioned before, because they are different than from those in conventional materials, so we expect also then these materials to have different mechanical properties, because as we mentioned before, the microstructure itself contains the state variables then for the constitutive laws that are going then to define the mechanical properties of the material. Saying that, so many strategies are being developed or are in development to mitigate detrimental effects of additive manufacturing. Nevertheless, as it would be the case also for conventional materials, controlling the microstructure during the processing is fundamental, since this also allows controlling the final properties of the material by means of the microstructure itself. And in this task, simulation can be very helpful, right? So because simply by changing the parameters of the simulation, the processing parameters in the experiment, so we can also realize many different microstructures, right? And because there's always a connection between the simulations and the experimentation, we expect then that these predictions is a faithful reproduction of what we can expect from the experiment, right? So this is not going to be always the case, right? So, but we can expect then that at least then the microstructure is going to reflect the most fundamental features that we can also expect in the experiment. Okay, so here in this slide, so we have then essentially the process of additive manufacturing. So we have a metallic powder, right? So then we have then certain process parameters which are utilized for the fabrication. There is certain temperature distribution caused then by the heat source. In this case, the laser is what we normally utilize for melting the powder, and then this is going to result in the formation of the microstructure. And the microstructure itself is going to determine then the mechanical properties. So what we would like to do is simply then by considering only then the processing parameter, we should be able then to finally predict also the mechanical properties, right? So that will be the final objective of this project. Okay. In any case, so what we did, so as I mentioned before, so we utilized first a crystal plasticity, or we developed a crystal plasticity finite element model for predicting the mechanical properties of the material. But as I mentioned also before, right, so it is necessary then also to be able then to simulate the microstructure development during additive manufacturing. To this aim, so we're utilizing a cellular automaton model. And in the cellular automaton model, so then a representative volume element, so a representative volume element, it is then the part of a component or the part of the material which it is going to better represent then the behavior of that material or the structure of that material, and it is the minimum volume that we can consider for this aim. Okay. In this case, so we subdivide that volume or discretize the volume into numerous cells, and these cells they can have different sizes, right? So usually we utilize cuboidal shapes in this case, so cuboidal cells, and each of these cells, so they can have different states. So these cells They can, for example, be a solid, right? So in the case of a crystal, right? So after solidification or during solidification, it can also be powder, right? So this is before the process begins. It can also be a liquid during the melting of the material, and it can also be a void or gas, right? So this is also to represent the porosity in the additive manufacturing process. Okay. Now, so once we have discretized the volume, which we are interested into simulating, so we also needed to apply a temperature field, right? So this is important because in the case of additive manufacturing, we have a very high heat source, right? So like the laser, and for that reason, then to be able to impose the temperature field on the microstructure field on the cellular automaton itself, so we need also to perform additional simulation, right? So the temperature, it would be almost impossible then to determine experimentally, right? So because we would require then to know the temperature at different positions of the representative volume element, and there are no instruments that can also measure with that high localized accuracy the temperature field, for example, right? So and to this aim, so we utilize also finite element simulation. So we pre-calculate then the temperature field imposed on the microstructure, and then we simply then couple together then these two types of simulation. Right? So on one hand, we simulate first the temperature, we impose the temperature onto the cellular automaton, and then that temperature is going then to influence first the melting of the powder, and second is also going then to cause the driving force for the crystallization and also then the growth of the crystal during solidification. There are two different physical mechanisms that are going to affect then the development of the microstructure during solidification. So the first one is nucleation, right? So nucleation is caused simply because when the temperature decreases after melting, there's also going to be a thermodynamic driving force for solidification, and then a certain parts of the representative volume element, so grains are going to start appearing, right? So crystals are start crystallizing, nucleating, and then if there is a high temperature gradient, right? So a driving force for solidification, these crystals they can also grow. Okay. Okay, and to do this, so in the model, so we need to separate these two different mechanisms, right? So on one hand, we need then to consider nucleation, and on the other hand, so we also need to impose a growth model then for the crystal growth during solidification. The nucleation model, it is usually then stochastic in nature, and the reason for this is because nucleation is a very complex process, right? So we consider two different nucleation mechanisms usually, which is also utilized or observed experimentally in additive manufacturing. So we consider epitaxial nucleation. Epitaxial nucleation occurs then along the solidification line, and this is normally then corresponds then to the grains that form at the border of the melt pool, and they grow in a directional way. In addition to that, so we can also consider bulk nucleation. This happens in the melt, and normally they have random orientations. In the case of epitaxial nucleation, the orientations of the grains are very directional. And then the microstructure, when the dominating mechanism is epitaxial nucleation, they are normally going to end up as a columnar microstructure. Okay, because we're considering here an stochastic process, so we need to consider also here then the nucleation number. Right? So this is the number of nuclei that we observe per unit volume in the melt pool. And for nucleation, we have to consider a probability of nucleation. This probability of nucleation depends then on the temperature gradient, right? So the larger the temperature difference between the current temperature and the melting point, the more likely it is the nucleation a nucleation event to happen. Okay. And once we have then these grains nucleating, so we also need then to consider now that also the difference of the temperature of a cell with respect to the melting point is also going then to cause then the growth of the crystal. Now, before we continue, we also have to discuss something that is very particular to additive manufacturing. And this is the case of remelting. So remelting happens in additive manufacturing because the laser can pass a position several times, right? So because there is simply then the melting of powder layer by layer, right? So it is also possible that one cell experiences more than once a temperature higher than the melting point, right? And this event is called a remelting event. So now the problem in simulations with remelting processes is that because when this happens, so we have then to reallocate and shuffle memory. And these two events, right, so regarding here the computational implementation of the model, they are very inefficient. Right? So, and this essentially means that that this is going to slow down the simulation. To avoid this, so what we're considering this is a different algorithm compared to those which have been implemented in literature. To begin with, so here we are showing here, for example, then an example of the temperature profile of one cell picked randomly, and we can observe here then that the temperature as a function of the time is going to experience two temperatures higher than the melting point, right? So here we have the liquidus temperature. So we observe then that at t equal to 0.01 approximately seconds, so we have then a melting event, right? However, right, so then once the temperature starts decreasing, right, so perhaps we have here nucleation in this cell. This nucleation is going to induce growth of the cells, but as time happens, right, so we observe that at different point in time, approximately 0.02 seconds, we are going to observe now here a new remelting process, right? So here the cell is going to remelt, right? So any growth that we observed before is going to disappear, right? So that memory has to be then reallocated, and this is going to cost more time, right? So for that reason, right? So then here solidification is going to happen again, right? So now because we don't have any further remelting process, right? So here then solidification is going to be permanent, right? So in the sense that during the additive manufacturing process, we're not going to observe the melting of the cell again. Okay. Um, Again, right, so this costs time, right? So this is what we would like then to avoid. So what we did is essentially then that we are going now then to utilize a different algorithm, as I mentioned before, and because we already have pre-calculated the temperature of each cell, so what we are going to do is simply go back in time. So we are going to track back the time of each cell, and we are going to set now then the point at which then solidification is going to be most likely. So this is the point of certain solidification, right? We don't know whether this cell is going to nucleate or not, because we need also then to consider that the cells are going to have different probabilities of nucleation, right? So we don't know whether this cell is going to nucleate or not, but we know that when this cell nucleates or solidifies, it can only happen after this time, right? So because only after this time, so we know now that any temperature that the cell experiences is going to be less than the melting temperature. Okay, so it can happen at this time, right? So because the cell needs to melt in order to solidify, but it can happen before, right? So because at this point, so the cell is going to experience because the temperature is higher, a remelting process. Okay, so this is what we are doing, and with this we are actually let's say improving the performance of the simulation model. Okay. In addition to that, right, so our model is also was implemented for parallel computer architecture. So this is also then to consider larger volumes of the representative volume element, and this allows simply then to increase the accuracy of the simulation model, right? So because with this, so we can also decrease the cell size, and by decreasing the cell size, so we can also then improve the resolution of the model, right? So and this essentially means that we can consider all of the microstructural features that influence the mechanical properties of the material, right? So we can even decrease then the cell size then to the size of expected particles, for example, second phase particles. Or if we desire so we can also increase the size of the simulation to consider even then the fabrication of a part, right? So like an engine and so on, right? So this is not necessary, right? So because we know that in most of the cases the properties of the materials they are contained within a certain volume. This volume corresponds then to the representative volume element, which by definition is supposed to be a minimum volume. Okay, but in any case, so we have here then the model is implemented in parallel, right? So we utilize here transfer of information across computational domains, and this information, right, so allows them to have a perfect coupling then between the computational domain so that the errors are kept to a minimum. Okay. Okay, so now I would like to show here the case of study. So what we are utilizing here to validate our simulation and also then to have an interesting case to study. So we're utilizing the aluminum scandium system, right? So this system is particularly interesting because these alloys could be used in the future by the automotive industry, for example. Scandium and aluminum, so they form second phases during solidification, right? And for that reason, the microstructures which are obtained after additive manufacturing are very complex. So these microstructures are characterized by a very fine grains, right? So, and in between these zones with very fine grains, so we have also columnar grains, right? So, and for that reason, the properties of these alloys are very particular, right? So in the sense of they are positively particular, right? So they show excellent mechanical properties. However, right, so this happens because at high temperature, right, so during solidification, there is a region where we observe then deformation of particles, the scandium, aluminum second phase particles, right? And because suddenly in the liquid, so we have also then here an additional phase at the surface of the particles and the liquid, so we also have then a reduced work of nucleation. So essentially this means that the probability of nucleation increases. And in any region where we observe a pronounced nucleation of particles, we are also going to observe a pronounced nucleation of crystal, right? So that solidification is going to result in these fine grain structures, as we are going to see also in the future. And we would like also to implement this into the models. To this end, so we utilize here a temperature to time transformation diagram based on a Abrami scheme to consider here then the probability of nucleating a particle of scandium and aluminum, right? So for example, right, so here we follow then the different cooling rates, right? So and then if we intersect or we pass across a zone where we observe the formation of an specific phase, then that the probability of nucleation of a particle is going to increase, right? And once we have considered then the nucleation of this particle, right, so then we can also consider an increased probability of a crystal nucleating there. Okay, and this is going to result then in very specific microstructure as we're going to see in the next slide. But before that, so as we mentioned before, so we are also then simulating the mechanical properties of the material, right? So because the aim of this project is then to simulate from the very beginning, from the processing parameters to the end to the final properties. So in that case, so we need also to correlate the microstructure that we simulated with the cellular automatic then to the final properties that it is simulated in this case by utilizing crystal plasticity model, right? So the crystal plasticity model I'm not going to explain further because this was already explained in the first part of this project. However, I will simply mention that we're utilizing also this model then to predict the mechanical properties of the material. And now to the results. So here we are going to observe on the top a result of the simulation, right? So and here at the bottom we can observe here then the experimental microstructure that we can obtain then after additive manufacturing. It is difficult to see here then those zones where we have a very fine grain structure. However, those zones they are in between here then the larger zones with columnar grains. So when we observe columnar grains, this essentially means that we didn't have nucleation of second phase particle, right? So because in that case, so the nucleation of grains during solidification has not been promoted, right? So and in those zones here at the intersection between columnar grain zones. So we observe this fine structure of grains, and in this zone, so we expect to see a higher density of second phase particles, right? And at each of these second phase particles, we expect to have one or more crystals nucleating, right? So simply because the work of nucleation is also being reduced. Okay. Here in the simulation, right, so we observe difficult to see, right, so in this case, so because we have also different representations here, but actually we have also a relatively good agreement then with the simulations. We can reproduce the fine grain zones. We can also reproduce here then the columnar grains. And simply here what we observe is that we are simulating only one part here of the process. The reason for this is very simply to understand, right? So if we try then to simulate the whole volume, it is possible to begin with, right? So, but in that case, we need then to utilize a very fine cell size, which has to be smaller than the smallest grain that we would like it to represent in the simulation. So for that reason, so we're simply simulating certain parts here of the melt pool, right? So also, we are doing this simply because we need also to transfer here then the three-dimensional information then from the cellular automaton model to the crystal plasticity model, right? And the crystal plasticity model is also limited by memory, right? So and for that reason, right, so we cannot then fully utilize all of the information then from one model into the other. So we need then to make here a simplification, right? So, and this simplification simply means that we need to utilize a smaller volume than the one that we can simulate in the cellular automaton, for example. Okay, so in any case here to the right, so we can observe here the results of the crystal plasticity model. So to begin with, so we can observe that there is a deviation between the simulated properties and the experimental one. So here we are seeing the stress strain and diagram. And the agreement is not really that bad, right? So here we are seeing a deviation of about perhaps 50 megapascal, which is not too good to say something. However, so we have to mention here that we are not considering all of the factors that influence the mechanical properties of the material. So for example, in the crystal plasticity model that we implemented, so we didn't take into account the effect of solid solutes, right? And by considering the effect of solid solutes, so we expect then that the differences here are going to be less than the ones which are indicated here. So the reason for this is simply because we didn't have time then to implement also the effect of solid solutes into our simulation. However, so we expect to improve this in the future, so we can also improve our results. Okay. To conclude, so we utilized here the crystal plasticity model to simulate the grain structure of the scandium aluminum alloy. So we observed the fine grain and also we observed the columnar grain. So the microstructural output was coupled with crystal plasticity finite element simulations, and we were able then to predict the mechanical properties of the material. Right? So future work includes to improve then the accuracy of the crystal plasticity simulations and also the cellular automaton. So I would like then to finalize this very short presentation, maybe not too short because this was supposed to be 10 minutes and this is now 30 minutes. But in any case, so if you have any questions, I would be very happy then to answer them. Okay. So thank you very much. Goodbye.